Good afternoon, everyone. When I was doing some research for my PhD, I came across some very interesting articles that were related to my research. And as I read more about the work of the researcher, I grew increasingly eager to meet the person behind the knowledge. Today, we are all fortunate enough to have the opportunity to meet him. It's my pleasure to welcome Professor Andreas Busch to our university. Professor Busch is a current researcher at Harvard University. His work focuses on the hydromechanical coupling in CO2 storage, unconventional and energy storage reservoirs, and reservoir fields as well. He's also involved in several national and international research projects, making him a well-respected figure in the field of geoenergy. About his educational biography, he got his diploma from the Phillips University in Marburg, his BSc in the University of Stellenbosch, PhD postdoc at the University of Aachen University, and he's worked in the industry at Global International, and he's been a professor of earth science and geoenergy at Harvard University since 2018. And now he's a Deputy Director of Research School of Energy Geoscience at Harvard University. Today, I'll be talking about multiphase flow and rock fracture, and can we predict fault leakage through upscaling? We are honored to have him here today, and we thank him for taking the time to come and share his expertise with us. We're extremely grateful for his contribution to the field and wish him all the best in his future endeavors.
Oh, thanks, Noah. That's about the best introduction I ever got. Really, really nice. Thanks a lot. So yeah, welcome everyone. Because I only see the people in the room. I was told there's people on Teams, there's people on YouTube. So seems like I'm becoming an influencer or something. So yeah, I mean the work that Noah was referring to that very much relates to unfractured rocks, mainly mud rocks. So looking at pore size characterization. I'm not going to talk about that today. So we've been working quite a bit on fractures over the last couple of years. Different topics, different ideas, different concepts, different lab methods, all with the goal to integrate that into modeling for upscaling, kind of being able to predict a long fault flow in subsurface storage reservoirs, for instance, can also be geothermal reservoirs that we're working on. But today I'm mainly talking about mud rocks, not so much the granites kind of things. I should probably get started with introducing a couple of people that actually did most of the work that will be shown today. Of course, hardly ever me. It's Georgi, who was just finishing a PhD on pore network modeling, but he did a lot of the image analysis that we get from micro-CT. Tom Phillips is a graduate from here, from Liverpool, so it's a former student of Richard, actually. He finished his PhD a couple of weeks or maybe 2 months ago on multiphase fracture flow, also single phase, but mainly multiphase. And Roberto and Nathaniel, they both used to be postdocs, the one looking at more fracture characterization and putting them into statistics. And Nathaniel, who's now an assistant professor with us, he has been looking into measuring fracture flow properties of all sorts of mud rocks, but with a focus really on Nash Point from Wales, because he's Welsh and the Welsh are very proud of their country. Good reason, I guess. I also work a lot. So I'm a geologist, so I'm not so much an engineer. I'm not so much the big modeler, which is why I work a lot with the Institute of Geoenergy Engineering on campus. That used to be the Institute of Petroleum Engineering. Obviously, even at university scale, you do a bit of greenwashing, not only in industry, but really doing our best to kind of shift from petroleum-related research into the more kind of green energy sources, which is actually working very well. I still work quite a bit with my former colleagues at Shell, and we worked a lot together with Ghent University in Belgium and the Swiss Light Source synchrotron imaging or for multiphase flow and fractures. And I hope didn't forget too many people. So let's start with a bit of an introduction. One of the best skills of Tom Phillips actually is drawing these sort of diagrams. And he did many of them, and I used them all really with pleasure in all the lectures and seminars. So this is from him, and it kind of shows a bit that where we are going at the moment. So we are of course transitioning from more fossil fuel based energy sources to more greener ones, and likewise academia is also transitioning all over the place. Some more, some less, but a lot of people that have worked in oil and gas in the past, they are nowadays working on topics such as carbon capture and storage. Hydrogen storage, underground storage is just starting as a research topic with relatively little to no field experience. And then we are also working on geothermal energy, which can be very shallow, down to a couple of 100 meters maybe, but can also be very deep. If you think about the deep geothermal wells down in Cornwall, the United Downs and the Eden projects that have drilled wells down to around 5 kilometers depth into granite. So this is really, really deep geothermal with temperatures of close to 200 degrees, where you're not only producing or where you're not only using that energy for heat, but you can actually also turn it into electricity. So these are the sort of topics, we also research topics that we are working on quite a bit. And one thing they all have a bit in common is fractures related to faults that can act as a leakage pathway towards the surface, or on the for the deep geothermal, they're actually the reservoir. So the fault zones are actually used for the fluids as to flow through and then to heat up. So for United Downs, for instance, the idea is to inject at 2.5 kilometers depth and then produce at 5. So you're producing a pressure gradient from top to bottom, and you aim at heating that up significantly. So we need to understand fractures much better than we are doing today, and we also need to integrate that knowledge into upscaled modeling. We of course cannot work on entire fault zones in the laboratory; they are simply too big. So, but we can work on fractured samples, either naturally fractures or induced fractures. Understand their behavior, and then come up with fracture networks that we then integrate into this modeling. So if we zoom in a little, and much of this will actually be more or less related to CO2, not so much to geothermal. Nathaniel is working a lot on geothermal, and we actually have a NERC project that is working on the deep geothermal, granite geothermal down in Cornwall. Also in collaboration with Dan and Michael to look at the fracture properties of that. And we run fracture flow experiments, these sort of things on these granites. But that is a different story, and that would probably best being told by Nathaniel and our PhD, Nick Harpers. So if we are looking at CO2 storage, for instance, we always need to keep in mind the risks. There have been a couple of reports published lately saying that the risks are actually marginal, which I would totally agree. But nonetheless, I think for each individual case study, there needs to be a proof what the risks actually are. And risk of leakage can be, again, case specific, but then can be through several different mechanisms. So one of them might be just through the matrix of the cap rock. So we get matrix flow, overcoming capillary entry pressures through these low permeability formations. And you might then get something like this scenario where the CO2 phase is displacing the water phase in the cap rock at high enough pressures, and then you get leakage. The permeability of that would still be very, very low. The gas saturation would be very, very low. So it is then something for kind of a reservoir model to identify what the sort of leakage rates could be. We can get chemical reactions in the subsurface, or something that Nura is working on, for instance. So how does injected CO2 that is then dissolving in the water phase, how is that reacting with the mineralogy of the cap rock, and how is that changing petrophysical properties like porosity and permeability, and with that then also potentially mechanical properties, and what sort of effect does that have on the cap rock integrity. Or we can leak along faults. Depending on the displacement, we can have small width fault zones, we can have large width fault zones, can have very intensely fractured fault zones, we can have self-sealing fault zones, and so on and so forth, very much dependent on burial history, on displacement, on the rock properties itself, the mechanical properties, the mineralogy, and so on and so forth. So this is something we need to understand. And I think we still have insufficient understanding of these sort of properties. And what I'm seeing at the moment is that in the future, there will be likely more CO2 storage projects into reservoirs that are actually fault bound in comparison to maybe big aquifers where that doesn't matter so much. How do we get there? That is the big question, really. And how do fracture properties change under the changing subsurface conditions? And with changing subsurface conditions, we can certainly identify the changes in pore pressure. So we are injecting CO2, we are increasing the pore pressure, we are decreasing the effective stress. We can have chemistry effects. So we can have, for instance, carbonate precipitation. So if you have leaking CO2-rich fluids, they migrate, to shallower depth, they decrease in pressure and temperature, which then ultimately results in a CO2X solution. So it's your Coke bottle, does similar things. With CO2X solution, we supersaturate potentially in carbonate and get precipitation. Might be a natural self-sealing effect in the fractures, decreasing the permeability and the leakage risks. And we found a third mechanism, which is still not 100% research, really, is the potential swelling of things like smectite, montmorillonite, when CO2 is entering the interlayer space of these smectites, and can potentially cause some swelling pressure. And the effect of that is still kind of debatable, but it isn't fully excluded as a mechanism that can impact fracture flow properties. Right, this is just a bit towards the introduction, and I think the next couple of slides will be really showing a couple of findings that we have in the lab, and discussing that and trying to put that into perspective when it comes to upscaled modeling. Right, so if we start with a natural fault, and I'm sure that most of you will know these sort of concepts. So this is redrawn from, I think, a very well cited publication. Forgot which one, but Tom has redrawn that. So this is a very simplified kind of fault zone where we have the fault core in the middle. We can have multiple fault cores, as a matter of fact. Fault cores are typically surrounded by a fracture network. That's our damage zone. And this fracture network can be very dense, but can also be very wide. So there can be certain numbers of fractures, maybe over a meter or something. And the crux is that the closer you're getting to the fault core, typically the higher your fracture density. So the more damage you have created, and the further away you get from your fault core, the lower your fracture density into the protolith, which is just naturally fractures, which might have fractures, but not through the faulting itself. So this is our reservoir in terms of geothermal energy, but this is also our concern when we are injecting CO2 or potentially also hydrogen. Can probably put that, yeah, good. So if we look at then these sort of features in a little bit more detail, then we bring it down to a single fracture. And this is the sort of scale that we can address in the laboratory. So we cannot look at the networks, but at single fractures. We can measure the permeability of these single fractures as a function of effective stress. So when we are changing the pore pressure, when we are changing the confinement, and typically what we see is that when the effective stress increases, the permeability is decreasing. But that curve that you see here can have a completely different shape depending on the rock type that you're looking at. So that's what we do in the lab. And then we need to prepare our findings towards the modeling. And that is a challenge in itself. In terms of modeling, typically fractures are treated as a parallel plate concept. So you're assuming two plane surfaces that have a certain distance from each other, which is the aperture. And the aperture width is then going into this very simplified equation, which gives you the flow rate through that fracture. And this is typically how fracture flow is modeled and can then also be incorporated into fault flow. But then again, we know that nature is a little bit more complicated than this, a little bit more complicated than an engineering concept. So we know that fractures have a certain roughness, so they're not just parallel plates. And the roughness then determines what the difference is in terms of the hydraulic aperture. That's the thing you see in blue in the middle, or the mechanical aperture, which can partly be larger than the hydraulic aperture. And this is very difficult to characterize, as a matter of fact. This is how it not only looks like in a drawing, this is how it looks like in real life. So this is a micro CT scan of an aperture. Think of a relatively strong kind of a cap rock from a natural CO2 reservoir in Utah, Carmel sample. And we find fractures at that sort of roughness at a bigger scale, also not being a straight line. So it's following a certain tortuosity. So a fracture isn't a straight line. It is typically tortuous, and depending on its tortuosity, of course, the travel path of any kind of fluid through that fracture will be longer or shorter, right? Depending on the complexity. What we also find quite regularly is, of course, that even though you have a fracture that might have a relatively high aperture at some point, it might be blocking at other points. So you can have touching points, and wherever you have touching points, of course, that is decreasing your flow rate. This is what we see all over the place. And this is, of course, also information that is not included in the relative simple parallel plate model. So it adds complexity, but then, of course, nowadays we have the advantage, which was probably not there 20 years ago, that we can image these sort of things, right? So we have micro CT scanners where we can get a static image. We get to see that. We can characterize the tortuosity. We can characterize the aperture field. We can put that into digital models. We can get 3D models of all this, and we can use these 3D models to actually then implement that into pore network or fracture network kind of modeling directly. We can also use these imaging techniques to then look at fluid transport through these fractures. So the only thing you need to do is you need to do it very rapidly, which is why we went to synchrotron, because lab-based micro-CT doesn't work in that sense. The synchrotron computer tomography, where you get scanning times of 2 seconds, then you can really look at real-time invasion of fluids into your fracture. And that's what we did, and that's something I'll show you in a bit. So the concept of that is, of course, and there we are again, the CO2 storage and the analogy to that, or hydrogen. We typically have a cap rock that is completely water saturated, not only the matrix, but also the fractures. So if you want to leak CO2, advective leakage, so CO2 as a fluid phase, then we need to displace the water in these fractures, right? That is happening at a certain gas saturation. The gas saturation is very much dependent on the gas pressure, on the capillary pressure of the fracture. Capillary pressure of the fracture, again, is very much dependent on the aperture. The smaller the aperture, the larger the capillary pressure that you need to displace the water in there. But you get an invading phase, that's your CO2, maybe hydrogen, and that is then displacing the water. This is in from a micro CT perspective. This is how it looks like with relatively long scanning times. But this is something we did as kind of pre-test for the synchrotron measurements. So we had this is the fracture only of whatever mud rock. That doesn't matter so much. We saturate that with water. Wherever there's white, there's touching points, right? So it's not a continuous phase across your fracture. So you have the upper fracture surface is touching the lower fracture surface, and then we are injecting, for instance, CO2, and we see how the CO2 is displacing the water within that fracture. And the more CO2 we are injecting, the more pore volumes we are injecting, the more of the water is then actually getting displaced. Right. That's for later, the multiphase. So we look a little bit at stress permeability. So I've shown these pictures again, but again, and why that is important is the stress permeability gives you a value for the permeability with changes in reservoir pore pressure. Right. So you're injecting CO2, you're continuously increasing the pore pressure, which means you're continuously changing the effective stress towards lower values. So you're basically pushing the fracture surface apart. So you're widening the aperture, and there's a relatively clear relationship between the aperture and the permeability. This is sort of measurements that we did, quite many. And we also used quite a few lab studies that were doing this. And what you see in this picture is a bit confusing. The next one will be a little bit clearer. So these are all lab measurements on cap rocks, so low permeability rocks, where the permeability has been measured against effective stress. And what you see, first of all, of course, is that there's a huge range in permeability values from close to Darcy, so 10 to the minus 12, down to something like close to nano Darcy, which is 10 to the minus 21. So we get 8-9 orders of magnitude difference for low permeability rock. So so we cannot just use a sample from field X and implement it into a reservoir model of field Y or Z. That just doesn't work. So we need to understand a little bit better of what the fracture behavior is. And there are very big differences simply because the cap rocks are very different in terms of the mineralogy and mechanical properties. But what we already see on the second view is that we get a certain class of behavior that produces relatively high permeabilities, like up here. So everything that has a higher permeability than 10 to the minus 16, for instance. So those are the more brittle or more stiff kind of cap rock samples. So they have a relatively high stiffness. And then we have those that have permeability, say, below 10 to the minus 17 down to 10 to the minus 20. And those behave very ductile or plastic and are actually very, very close to the matrix permeability. So this is what we would consider self-sealing as a risk scenario, and this is what we would call rather brittle, rather conductive. So these sort of cap rocks might imply a certain risk for CO2 or other fluids to leak. The reason for that is, of course, first of all, effective normal stress. So this is a more diagram. Shear stress against effective normal stress. I'm sure you all know that. Working with Dan, I guess, so that means you probably know that better than me. But we can have different types of fracturing, more shear fracturing, more tensile fracturing. So from mode 1 down to mode 2 kind of fractures. And depending on what the shear stress against the effective normal stress is, we create different scenarios in the subsurface to create self-sealing or not self-sealing conditions. And on top of that, it is very important what the sort of clay mineral content of the sort of cap rocks is. And I mean, it can be anything. I mean, there's people that call a cap rock when it has 20% clay. And in other cases, you can have easily up to 70% clay. And that, of course, makes a big difference. And there's a very nice study of Ian Bourke think he's now at Princeton, who looked at all sorts of analog kind of cases all around the world to see what sort of catwalks are actually leaking or not leaking under field conditions. And he found that those that are where the main load is actually carried by the clay minerals, those are actually sealing. So when you have a high clay content, it's very likely that the fractures are sealing in comparison to where the load of the rock is more carried by more rigid grains like quartz, feldspars, maybe carbonates. Then it can be more likely that the formation is leaking. Right, so we can parameterize permeability stress relationships. So there's a couple of equations to actually do that. We did that with this sort of equation. It's not so important where that is coming from, but of course it gives you a bit of cleaner lines than these weird, funny laboratory data points. And again, we nicely see these two different classes of rocks. So those that are more brittle have a high permeability, and those that are a little bit more ductile with a low permeability. You see the permeability values in here being much higher than 2 slides earlier. And the reason is that this has been measured on a plug scale. And this is then recalculated on the fracture only scale, right? So this is really only the flow through the fracture and not through the entire plug, with the assumption that the matrix has, in comparison, a 0 permeability, which is actually quite nice. So that's probably the only thing that makes this sort of work easier for cap rocks compared to reservoir rocks. You can assume that the matrix has a 0 permeability, especially in relation to the permeability to the fracture. What we then also found is that we get a very nice relationship between the fracture permeability and Young's modulus. So the stronger the rock, in fact, is, the higher the likelihood that the fractures would be leaking. And you can, of course, also make, again, a relationship then probably towards clay mineral content, but we couldn't find that value for all the literature sources that we have. But in most of the cases, there was Young's modulus, and you find this very nice relationship, plus or minus, for exactly this. Right. So this is this was a bit fracture permeability in the more generalized terms. We then can also have a look at anisotropy, right? So all the studies that have been published, I think most of them don't even mention what the fracture angle to bedding actually is, and in some cases it might matter, in some cases it might not matter. But that is, of course, a little bit of an unknown that we need to have a look at. So especially Nathaniel Forbes-Inskip, he had a look at anisotropy. So how does anisotropy of fracture orientation relate to fracture permeability? So, and as I said, he's Welsh, so he went down there to have a look at Nash point samples. I wonder if you call them shale. They're actually quite carbonate rich, so they're very strong. Advantages and disadvantages again. The advantage is it's easy to drill plugs. They don't fall apart like many others of this sort of material. But the disadvantage is you can always question if that sort of rock would actually form a proper cap rock above a CO2 storage reservoir. But of course, for the sake of looking at anisotropy, was a very nice case study, and that kind of emerged from his PhD that we then, continued a little bit to look into anisotropy. And what you see here is, and I think you see same sort of patterns also down at Kimmeridge Bay, where you have the fracturing, typically at right angles, happening within this formation. As I said, very carbonate rich. Don't ask me what the clay mineral content is. But what Nathaniel did was, in fact, looking at the different directions to bedding, and then all the angles in between. I think he had like 20 samples every 5 degrees. He had kind of a sample. Because we had to pay for all the micro CT scanning, we said we only do a couple of them and not all of them, because that takes quite a while. So that is pretty much anisotropy. Do you have fractures that are parallel to bedding? Do you have fractures that are normal to bedding? Or do you have this kind of in-between form? And how does that control fluid flow? And what sort of other effects does that have? So starting with that, and I think this is still from Nathaniel's PhD back at Royal Holloway, is that he created artificial fractures, so Brazilian tests, and he determined the tensile strength of this material for all the different angles that you have. And you see that you see again the different directions to bedding. So the short traverse, the arrestor, and the divider. You see the same again on this plot. This is the short traverse. This is the arrestor. This is the divider. And you see a couple of angles in between. And what he sees is that from the short traverse to the divider, we see an increase in tensile strength from Brazilian testing. What we then did is determining, and I think I haven't explained that, is the joint roughness coefficient. So it is a value that tells you a little bit about the complexity in fracture roughness. So the higher the joint roughness coefficient, the more rough it actually is, which means probably the less touching points, but probably also the stronger the material and the higher the permeability the fracture would be. So this is typically a measurement that you do under the microscope. You can also do photogrammetry, but there is also specific microscopes that basically measure the surface profile of a fracture, right? A profilometer would be another method. And then you can use some fancy Python code to statistically evaluate that surface roughness profile and come out with a joint roughness coefficient. That's what we did, and found that, again, the joint roughness coefficient, so that basically the fractures are becoming more rough, the higher the angle to bedding would be. But the difference isn't very big. So you see that it's now here jumping from 10 to maybe 12 or 13. This is not a big change. But for the divider, there's a huge difference, jumping from 10 to 30, so a factor 3. This is only one of the measurements, so that's something we would probably need to repeat with other rocks to kind of verify that this is not kind of an outlier or an artifact or whatever, but it seems to make sense. We then did micro-CT scanning, so and extracted the fracture from the samples because we're interested in the tortuosity. So tortuosity of 1 is a straight line. And every value that is bigger than 1 is taking a little detour, right? So, and you see that little detour here in the fracture. Matrix permeability, you would have tortuosities of 5, 10, 15 or something. And fractures, you see that here, you vary between 1 and maybe 1.1. So the difference isn't very big. You might get a 5 to 10% longer transport pathway, but that's pretty much it. But what we see is that the tortuosity is increasing towards a value of 45 degrees to bedding, and is then decreasing again. So there seems to be some sort of systematic in there. And that, of course, has an effect on permeability. While I would say, okay, I mean, that difference is probably not making a big difference. What we then also did, and this is also information we can get from micro-CT scanning, is determine the surface area. The surface area, of course, should be linked to the roughness. The higher the complexity of the surface roughness, probably the higher the surface area. That's what we see. So we see an increase in the roughness, and we also see an increase in the surface area, these sort of rocks, quite linearly. And then again, we see this jump for the divider position. And we then measured the permeability as a function of effective normal stress. And we were hoping to see a similar relationship, but we just didn't. So with all this characterization of surface area, tortuosity, tensile strength, and what have you, we didn't see any systematics in the permeability. So these were gas permeability tests, all following the same protocols. all staying in the apparatus for pre-stressing for the same time. And then measuring gas permeability with nitrogen, I think, and then Klinkenberg correction for 5 different pore pressures. But it is relatively chaotic what we see in there, so no real systematic. So this is something that we continue working on, I think, to better understand exactly these systematics, and then to see what sort of significance it would have for modeling flow through faults. Right. There was all single phase. And I would have had many more slides on many more other things, but would actually be nice to look at multi-phase flow. And this mainly relates to Tom Phillips' PhD, and he did a dual PhD with Ghent, so with Verle Knudde and Ghent, and they are very specialized on micro-CT imaging. Tom started off with printed fractures that had a defined surface roughness, so that is work that has been published. And then because of the pandemic, you only got the beam time at the synchrotron source very late. So the only thing you could extract before finishing his PhD is a little piece of it. But I think we have like 100 terabyte data that hasn't been looked at yet. And this is a little part of it. So what we know, or what we already learned, is that fractures exhibit surface roughness to a very variable degree, and that results in aperture structure. And what we wanted to look at is how this aperture structure is actually controlling fluid invasion and fluid percolation through the fracture, and how does that look like in pretty much 4D experiments. And what you see down here is the different flow mechanisms that you can have. So you can have some sort of viscous fingering. So yellow would be, for instance, CO2. Blue would be water. So you can have little fingers that are connecting from the one side to the others. You can have big patches that are connecting or forming big clusters that might or might not be connected with each other. Or you can have a very stable displacement front that is moving across your fracture. And all that, first of all, determines the permeability of the gas phase to the water. But it also kind of determines a little bit the time it takes to get from the one side to the other, or from the bottom to the top of the catwalk. So what sort of displacement do you actually get? And we found that this is very much dependent on the aperture field. So a bit experimental, and that already was a bit of a challenge. So we looked at a little bit more. So we looked at several samples, and this is only like an example for one of these samples. We looked at a little bit more competent kind of catwalk. So it's natural fractures that we plugged. And you see the various attempts here. So this is 0.6 centimeter diameter sample, so very small. We drilled several ones because it's very difficult to then not break the natural fracture. So some of them went wrong because they had little breakouts, or they had multiple fractures. But then eventually we found one sample that had just the right properties. We scanned that in micro-CT, so lab-based micro-CT, to verify that it's a single fracture, no breakouts all across the sample, and so on and so forth. So we injected water to see if we can see the contrast, and also to verify if we actually get water into the matrix, which we didn't see. So we only see water being in the fracture. We also injected decane, so it is actually a water and decane experiment. So we use decane as an analog fluid to CO2. CO2 would have significantly made these experiments more complicated. But you can use decane, where you know interfacial tension and contact angle, and then always relate back to CO2 experiments. Then we went to synchrotron with this sort of setup. So this is the entire sample scanned 18 millimeters long, 6 millimeters wide. It's the same for all the other samples that we scanned. It's a relatively complicated setup with fore pressure, back pressure, confining, and so on and so forth. We used very, very low flow rates, so 200 nanoliters per minute, to match with the scanning time. So you want to see how the fluid is invading over the sample, and not when you're finished with scanning that the fluid has basically passed all across the sample already. So you guarantee that with relatively low scanning times, and we used an effective stress of 25 bar. I think the pore pressure across the sample was 10 bar, which makes the confining pressure 35 bar. This is the facility. Maybe some of you have already been there. That's a Swiss light source, and obviously in Switzerland. And we had like 4 or 5 days to scan all the different samples. So drainage is when non-wetting phase is displacing wetting phase. So decane CO2 displacing water, and also imbibition when the water is then displacing decane CO2. So decane as our analog fluid. So we did these sort of cycles. But in the first kind of evaluation, we only looked at drainage, so displacement. So what does the leakage process look like? So that means for each sample, we had a continuous imaging over 150 minutes with a voxel size of 2.75 microns and a scan time of 1 second. That's the advantage of synchrotron. It's just more energy, right? So you very quickly scan, and then 2 more seconds for the source to return back to the initial position. So that makes it basically every 3 seconds we can do a scan. That's good and that's bad. Of course, you get very high resolution scanning. That's good. Bad thing is that that produces so much data that it, I think Tom in the end broke the processor of the workstation, because he was passing, I don't know, terabytes over that computer to actually put it on a backup. Now he left, of course, typical thing, and I can deal with the repairments. No, but that's it's simply the way it is. It's, I think, produced 160 terabytes of data, quite a lot. And what we see is, of course, first of all, saturate the fracture with brine, and then displace the brine with oil, which you see here in the first image. Right. What we are after a bit is more kind of observational to begin with. So how does that look like? How is non-wetting phase displacing wetting phase? And how does that relate to the roughness? So do you get different mechanisms where the aperture is larger and smaller, where it's more rough or less rough? And how does that look like? Do we get continuous phase across the sample, or do we inject in pulses and we get snap-off, and non-wetting phase fluid is kind of trapped at different places within the fractured field, and so on and so forth. And there's a couple of ideas of how that works, but I think these have been the first kind of experiments to actually show that in 4D, as far as I know, at least under this resolution. So what we see, or what we did, first of all, is looking at the aperture. So what is our aperture distribution? It's not exactly Gaussian. So we have a lot of small apertures, and then maybe it's a half Gaussian, whatever, and not so many very large apertures, or distances between the two different sides of the fracture. And this is something that is something that we are getting out of these sort of images. So this is the aperture in different color coding. So blue meaning small aperture, and towards the brighter colors or the warmer colors, we get larger apertures. So we see that most of these fractures relatively low apertures, maybe below 50 micron, which is already quite a bit. And then we have a couple of parts where the aperture is actually much bigger. We have the macroscopic flow direction from the bottom to the top. And what we see here is blue is the wetting phase. So this is water, and that is then getting displaced by the non-wetting phase here in red. And what you already see here is that we get patches, so we don't get a continuous non-wetting phase across the fracture. It's a bit counterintuitive, of course. So you would think if you're injecting fluid into a water-saturated sample, you would get continuous phase, but this is not how that works. So you typically overcome a certain energy barrier, and then you're basically passing a certain pore fault, you would say, in the matrix, right? So you're overcoming a certain capillary pressure, and then you get what we call a Haynes jump. So it's an energy barrier, and non-wetting phase is then moving from one pore or one part of the fracture to the next part of the fracture in a millisecond event, so something we cannot resolve experimentally. Not in this experiment, it has been done in other experiments, but that wasn't the focus. And if you do that, then you get to see these kind of patches of non-wetting phase, which is discontinuous. As long as it's discontinuous, we don't get leakage, right? We only get leakage if it is continuous advective kind of phase across the sample. So that has been done over time, of course. So that's how you get to 4D. So we start injecting fluid. We're injecting more and more fluid to a certain amount of pore volumes. And over time, we see obviously an increase in the amount of non-wetting phase. And you see that up here. So where we have these individual clusters, these individual clusters start to grow and to grow and to grow. And at a point, might not, now I can move this, right? At the point, these clusters, of course, as they get bigger, they also get closer to each other. And at a point, they start connecting. And when they start connecting, then, of course, we get a continuous phase across the fracture. And this is then when we start getting leakage. So what Tom has done is plotting all this. So he has identified the individual clusters that you see here in red, right? So we get kind of a linear relationship of the individual clusters with time or with pore volume of non-wetting phase that has been injected. We also get to see the fractal dimensions, that is the complexity of the individual clusters. So say the more complex, the higher the fractal dimension. And yeah, that's pretty much what we see. And this is very much contradicting theory. So theory would be that we relatively early start with a continuous phase. So that's what we call percolation, invasion percolation. So percolation theory, that with time, we are not increasing the number of individual clusters, but we are decreasing the number of individual clusters, and then basically have a more kind of stable displacement of the wetting phase across the fracture length. And this kind of clearly contradicts that, because all these little patches remain unconnected under the experimental conditions that we used. This is for the entire fracture, of course. We can, of course, now also zoom in and look at individual parts of it. This is something that Tom has also been done. So he has looked at certain parts of the fractures to basically identify what is happening there in terms of continuous phase, Snapoff, and so on and so forth. So CF stands for continuous phase, and SO stands for Snapoff, and I'll show you in a bit what that actually means. So this is connected flow, so really zooming in into smaller areas of the fracture. And there you pretty much see that you start with individual cluster, but then you start extending that individual cluster and you grow it, right? So starting point is that cluster, and then it grows first and foremost into the direction of the pressure gradient, but then also in other areas depending on the aperture field. And this is with time, of course, and which with time always means with increasing amount of non-wetting phase that has been injected. Other parts are very different. So where we see snap-off events. So the upper case, for instance, is we first start creating a continuous phase, but then we see that this continuous phase starts to break up. So we have snap-off events, and the moment there's snap-off between the two, then both of them are pretty much isolated and would be stagnant. So they wouldn't flow any further, right? So in CO2 storage, you would pretty much call it residual trapping. So it's you can see that up here. It's of course a little bit nicer here because the individual clusters are round. So you see that growing and it's growing and it's growing, and then you get this snap-off event. And we see these snap-off events because we then see small little jumps in the differential pressure across the sample, really kilobar, not kilobar, millibar kind of scale. So very, very small little pressure changes, and this is the energy that is then released through these snap-off events, where we see small little pressure decreases happening. And to complete that, this is in 4D, so that's one of the videos that we got. There's a couple of them. I think they're all uploaded to a publicly accessible GitHub, I think it is. So you see the development of the individual clusters. So this is decane. I'm really only focusing on decane, completely surrounded by water. And you see the different clusters developing over time. How long that goes, quite a bit. And as you can imagine, if these Haynes jumps, or these snap-off events, they're really milliseconds. But of course, a scanning cycle is 3 seconds, so we cannot visualize those really. And whenever you see little jumps in these pictures, this is really because it's 3 seconds is a frame, right? So this is not continuous. It's not a Hollywood movie. Right? How do we do? Oh yeah. Okay, I probably skipped that and would really like to show you a couple of slides, not many, on what we do with all that information, which is pretty much the key. So we used to have a relatively large EU project with academia and industry, where we developed a workflow of how can we scale up from lab towards field, outcrop scale to reservoir scale. Right, which is at the end of the day, which is what we need, right? So we want to understand what the potential fault flow rates would be in a reservoir. And obviously we measure the fracture permeabilities in the lab with the roughnesses and all that comes with it. I mean, all very academic. Only part of it can actually be utilized in any kind of model. Then we go into the field and we characterize fracture networks or fault zones, which is very challenging for mud rocks because they tend to weather quite significantly. It's very difficult to find places where you can actually do that. But if we get the networks and the statistics of that, we can incorporate that into hydromechanical models, match that with the permeability stress relationships, and then model the permeability on the fracture network scale. And the output of that would then go into the reservoir model as a single permeability. So the reservoir models, they're so big, they cannot address the very, very small fracture scale kind of sizes. So it needs to come as a single value. Modeling that, we did that for the North Sea. I think that remains unpublished. And that gives you an indication of what the fault leakage rates could be. And these leakage rates you then need to match with the potential monitoring tools that are available. So are the leakage rates so low that you could actually not see them with pressure, temperature, whatever, saturation sensors and these sort of things, then it's not worth monitoring that. And if you have a better confidence of this relationship, potential leak rates, monitoring sensitivity, I think it can save us a lot of cost in deciding for the monitoring tools that are actually useful. But we are not there yet, really. No, this one. Right. So for that, we went to a couple of places. I wouldn't say all around the world, because the only one not in Europe is Brazil. So we tried to find good places where we could get fracture networks in mud rock. So we went to Brazil to look at relatively low permeability laminated carbonates, which might also be a good analog for the North Sea, because some of the cap rocks are actually very carbonate rich. We looked at Mercia, we looked at Kimmeridge. In the UK, we worked with the university in Spitsbergen, because they have a very nice fault zone there that is most of the year deep frozen, so that prevents it from weathering. That is Conusdalen, working on a paper on this. We looked at the fault zone in Utah, which is naturally CO2 leaking. So there's a lot of data on that available already. And we have 300 meters of core that we once drilled into the fault zone. And of course, the best analog that I found so far is Switzerland, in one of their underground research labs, that is the Montrealab laboratory, where they have tested radioactive waste disposal. And they're very nicely a fault zone exposed there in galleries. So you get 4 little windows of how the fault zone looks like on a meter scale. So this is the first one that we actually use to get statistics of, because the Swiss Geological Survey nicely mapped all this for us already. So the only thing we had to do was actually digitizing that. So Montrealab, if you ever get there, you can easily visit it. It's really, really worthwhile. It's in the Jura Mountains in the northwest of Switzerland. And they have a motorway tunnel. And from the motorway tunnel, they drilled a couple of side tunnels for doing research, all sorts of things. And these are the 4 different snapshots of the Opalino shale main fault that you see there, with this fracture network in a mud rock of 60–70% clay. So what we did is digitizing the fracture network, where we get the different trace length, where we get the directions of the individual fractures, where we get the connectivity between the individual fractures. So that is the I, X, and Y nodes that we have, and we can put them into nice triangular diagrams. But the main thing really is, we also get the fracture intensity and the fracture density of this sort of formation. But most of all, we get a digitized fracture network that we can then use to implement into hydromechanical models. I showed this earlier. We have data of that formation. So what is the stress permeability relationship? We can plate that network with Opalino shale, so basically the formation that hosts the fault zone. We can also play that with other relationships, which is pretty much a scaling relationship, but not more than that. And then we would get that integrated into the model. So this is what the work that we are doing with the Institute of Geoenergy Engineering. Florian Doster there, he's using MRST that's developed by Synchrotron. It's the MATLAB-based reservoir simulation toolbox, open source, and very nice to work with. So we use the fracture network as a starting point. We can calculate contact stresses. I mean, each fracture at a different angle has different contact stress. We get the aperture, and of course we get the permeability out of this, and we can then match the model permeability with permeability they have measured in situ. So there have been wells that have been drilled into the fault zone, water has been injected, and the permeability has been determined. We did that for the Monterey case study. We also did that for the Utah case study, where we have some idea of what the actual fault permeability would be. So these are the kind of case studies where you do verification. And at the moment, we do a similar case study for Conusdalen and Spitsbergen, but there we don't have fault permeability for verification. So that is pretty much the workflow. I hope there will be a couple of PhD students to come to actually test that on different case studies in the future. But of course, it makes sense to get these sort of values. I mean, it's not only for monitoring, but what we also need to determine is like what is the risk of leaking fluids for shallow subsurface formation. So the moment we are getting into the drinking water aquifers, then we might get into an issue. The moment we are getting to a sea bottom or to the land surface, we want to know what the leakage rates would potentially be and how we could address them. Can we measure that at the surface? Can we monitor that or not? What is the likelihood of dissolution and dissipation in shallow aquifers, which very much depends on the flow rates. So how much can be taken up by an aquifer above the primary catwalk of our CO2 storage site, and so on and so forth. So this is work for the future. And then I probably conclude with a summary. So at least my opinion is that we are still falling very short in the understanding of flow and rough fractures. So there's a lot of mathematical concepts out there, but I mean, as always, we need to verify these mathematical concepts. With the lab techniques that we have, we're getting better because we can now image, right? So measuring a permeability today is done the same way as 50 years ago, but the imaging of all this is of course a significant improvement of what we can do. And if you get better in resolution, then we also of course getting better in the small little aperture changes that we have. So I think of combination of fracture characterization, classical hydromechanical lab tests, imaging, multiphase flow test, and ideally upscale modeling would certainly support the understanding of fault leakage. So we have to better understand the interplay between surface roughness, ductility, tortuosity, anisotropy, and so forth to determine flowing rough fractures. What is really like a bummer is that shale is not sandstone pretty much when it comes to outcrops, right? So whenever we go to an outcrop that is shale based, it will be weathered. You hardly see anything. So best places are still at the coast, or you need to go to underground labs or deep frozen or whatever, or quarries, things like that. But it remains really difficult to get a big range of outcrop examples where you can do then the field work and then the lab tests and then feed that into modeling. So this remains an issue. So if you guys know of good locations, let me know. And finally, upscale modeling. As I often see a big detachment between the people that are doing the modeling and those that are doing the observations. And I think that is another big challenge. I don't think that the modeling works without the observations, and I don't think that the observations work without the modeling. People that think they don't need a lab data point because they can model everything, that is a little bit out of this world. I sometimes have the impression. So that works very well for the work that we are doing with the engineers in the Institute of Geoenergy Engineering. But we also need to drag the engineers into the field to show them what we actually observe and how complex that is. So that is of course key. Not overwhelming the engineers. So the engineers should never overwhelm the geologists with math, and the geologists should never overwhelm the engineers with hugging rocks and these sort of things. But I think if there's good relationships, I think that will really progress this field of research. So yeah, that's it. Thanks a lot. See, I prepared for 45 minutes and then was again more than an hour. Should really work on my timekeeping. No, I mean, we still keep it with dimensions. So permeability, square meters, right? Because that's what we measure first and foremost. I think making that dimensionless, find that difficult and would leave that to others. So I mean, we really produce the data, but I think then when it comes to flow rates, capillary numbers, Reynolds numbers, these sort of things in the reservoir, that then really needs to come from an initial reservoir model, where you get an idea of you have a reservoir, you're injecting a certain amount, and it then tells you what the flow rate could be. So that's we use that then as a basis to do, for instance, these synchrotron-based multiphase flow experiments, which were really done under extremely low capillary numbers, 10 to the -7, 10 to the -8, with the assumption that when we would start leaking CO2, it would be an extremely slow process. Right? A very, very small gas phase to begin with, and then you build that up slowly over time. Obviously, when we are leaking CO2, potentially leaking CO2, it's not something that is happening on the order of hours. It will be years and 10 years and hundreds of years and maybe even longer, but it will be very, very slow.